are Team 19089, Microfluidic System for Determination of Platelet Stiffness. My name is Cody McDonald. I'm an electrical engineer and the team leader.
My name is Andrea Villaseñor, and I'm an electrical engineer.
My name's John Mack, and I'm an optical engineer.
My name is Hunter Spallis, and I'm a biomedical engineer.
My name is Martin Nimick, and I'm a biomedical engineering student.
My name is Sil Gopal, and I'm a biomedical engineer.
The goal of this senior design project was to design and build point-of-care microfluidic-based testbed for analysis of platelet stiffness. Stiffness is an important mechanical parameter of platelets in their activation and thrombotic events. Many circulatory support implants are limited by pump-related thrombosis. These devices expose platelets to unnaturally high shear stress compared to healthy arteries. This unnaturally high shear stress induces thrombosis, which can lead to major problems such as pump failure and even death. The Slepian lab is currently working on mechanoceuticals, pharmaceuticals which can increase the elasticity of cells, thus reducing the effective shear stress and the likelihood of a thrombotic event. Our system simplifies the process of evaluating the effects of mechanoceutical drugs in vitro. This will enable the rapid and efficient development of mechanoceuticals, leading to improved patient outcomes and potentially saving lives.
Here's how the system works. Platelets labeled with a fluorescent dye are placed on a glass slide between two electrodes. A glass cover slip is placed on top so that the platelets can be imaged with an oil immersion lens. To do the analysis, individual platelets are trapped between two teeth of the electrodes by applying a strong oscillating electric field of 90 to 150 volts. Once the platelets have been placed between the teeth, the electric field is dropped down, then stepped up in increments of 9 to 15 volts. Each time the voltage is stepped, the platelets deform slightly via a phenomenon known as dielectrophoresis. This deformation is captured by the system's camera, producing images which can be analyzed on an external computer by existing techniques. Since we know what force we are applying to the platelets via the electric field, we can use information about the deformation of the platelets and the force applied to create a stress versus strain plot from which Young's modulus, a measure of stiffness, can be derived.
Our objectives for this project include capturing images of platelets with 100 nanometer spatial resolution,
Replicate the illumination capabilities of expensive fluorescent microscopy systems using affordable and easily available components.
Our system needed to be compact and portable. We achieved this by creating a lightweight, space-efficient housing box out of acrylic sheets to isolate our system from ambient light. Another goal was to create a user-friendly system, which our housing accommodates by shielding users from electrical components.
The existing system uses a full-size function generator, power amplifier, and oscilloscope in order to create and measure the system used for dielectrophoresis. Our goal is to design a system that integrates these components into a much smaller, more portable package.
So what we did is we incorporated the features that were used from those systems into one circuit design.
Our approach to the problem was to divide the system into two separate subsystems, the function generator and power amplifier. The function generator circuit is responsible for producing the oscillating signal at 1 MHz between 0 to 6 volts peak to peak. The input to the function generator is a PWM signal produced by the Arduino, which is controlled with simple software. Each PWM output corresponds to a different voltage level output by the function generator. The power amplifier circuit takes the signal produced by the function generator as an input and steps it up to 0 to 150 volts peak to peak. We use PSpice to simulate and verify our electrical system. Our simulated output produces each 15-volt increment within a 5% margin of error.
This image shows the prototype for the assembly of the entire electrical system. The circuit is housed in a 3D printed case that allows the system to be isolated and portable.
System requirements for the electrical subsystem were the generation of a 0 to 150 volts peak to peak 1 MHz signal at 15 volt increments with 5% margin of error. These tables show that the outputs of our electrical simulation were all within the 5% margin of error of the desired values, satisfying our accuracy requirements.
The electrical system is also required to be powered by a wall outlet and include an emergency off switch. We used a GFCI plug to connect the circuit to the wall that immediately cuts power to the system in the event of a short circuit, satisfying the safety requirement. Eagle was used to design a printed circuit board for the entire system, allowing for easy assembly and reproducibility. Outputs to power the Arduino and the LEDs associated with the illumination system are included in the design. Unfortunately, due to the COVID-19 pandemic, the testing and verification of the assembled system has not been completed. An ECR was submitted to change the project scope to reflect what we were able to produce with the resources available, a simulated design that meets our requirements. We are confident that the system would have been successfully completed under different circumstances.
The components used for our Illumination Subsystem include a blue LED, a bright field LED, a dichroic mirror, a FITSI emission filter, and a collimator lens. The following simplified point design shows the pathways of light traveling throughout our system. As you can see, the wavelength range of our blue LED is 465 to 485 nanometers. For the entire range of dominant wavelengths, which the LED may emit, reflectance at the dichroic should be about 100%, meaning that very little noisy wavelengths will be erroneously transmitted through the dichroic to the sensor. Based on the dominant wavelength emitted by the LED, the percent normalized excitation may be larger or smaller. We decided to test multiple LEDs and choose the specific diode possessing the most optimal dominant wavelength for activation of Alexa Fluor 488 dye. From there, our tag sample will emit a wavelength of around 525 nanometers. About 95% of light will be transmitted through the dichroic, ensuring a strong signal from the sample. This figure shows that the emission filter will not significantly attenuate signal wavelengths, and may additionally aid in filtering any stray noise wavelengths that may have passed through the dichroic mirror. Using low-cost LEDs, switches, and potentiometers, we created a system that allows the user to easily switch between a fluorescence imaging mode and a bright field imaging mode with smooth dimming controls.
Using geometric optics modeling, we determined that the highest optical resolution we could achieve was 210 nanometers. To compensate for this, we resolved to oversample our images with an image sensor whose spatial resolution is over twice the Nyquist frequency. Pictured here are 100 nanometer polystyrene beads, imaged with the Slepian Lab objective lens and our team's objective lens. Some of the beads are circled in red. Both images were captured using the same image sensor. This image proves that our objective has resolving power equivalent to the Slepian Lab's objective. We used the tube lens, image sensor, and their respective mechanical housings to capture an image approximately 5.3 meters from the setup. This distance approximates collimated light, which is what the tube lens will image when used in conjunction with the objective lens. This test demonstrates the mechanical spacing and precision of our housing is optically adequate. From this test, we also determined that the depth of field of our tube lens is 381 millimeters. This is over 7 times what we require for use with our objective lens.
Here is a bright field image of the electrode captured with our assembled microscope. The distance between the teeth is 10 microns for scale. This image demonstrates that our system has the correct field of view needed for platelet electrodeformation experiments.
Throughout the semester, we have learned a lot of lessons through trial and error. Some of these include to always check our order to ensure the right parts have arrived, always ground yourself when testing circuits, and always ensure that all components have been discharged before touching them.
Due to the interdependent nature of the illumination, imaging, and housing subassemblies, we learned the importance of good communication and delegation.
For the mechanical subsystem, we learned how important it is to start prototyping as soon as possible in order to test our tolerances. A lot of 3D printers have sensitive printing cores, so starting early would have allowed us to decide on a filament and printer before printing too many components.
This concludes our presentation. Thank you to everyone who helped our team make this project happen.